So, we end up usually using either Professor McDonald's software or linear KKT. We have also developed our own software, but without any extrapolation, and it does the trapezoidal integral. What you should probably do to understand this idea well is to write a program to calculate the real part and imaginary part from a given data set for at least one point. That is, you have the equations for the integration, do numerical integration. Okay. So, you will be able to understand what goes in there and what are the challenges. Look at the formula, it looks okay, I need to use the formula and get the result, whereas actually use the formula, you will know whether there are any difficulties in using it. Okay. Then you would know when somebody gives you a software, they have done some calculation in certain areas. For example, you might see a place where you get 0 by 0. Okay. So, the equation looks like z real at x, z real at omega, x minus omega. So, when x equal to omega, it will look like 0 by 0, correct. Okay. But it is not a singularity, this singularity can be removed, and it is not that difficult to work with, but I would like you to try evaluating the integral, KKT integral, then you will really know, okay, this is how it is done, this is what we are getting out of it. So, next I want to go through analysis. So, what you have seen so far is I want to validate the data, I do not worry whether I have to use 10 white elements or 1 white element, I just want to know whether the data is valid or not. Now, I want to show you an analysis where you can use circuits and say this circuit can produce this spectrum. I can use the circuit to get some physical meaning out of this system. Okay. Ultimately, circuit is still an analogy, okay. But earlier I have shown that you have an electrode, you have an electrolyte, you have a reference electrode here, and you can represent the electrolyte using a simple resistor. This forms a double layer, I can represent that by a capacitor. If there are reactions here, I can represent that by some sort of impedance. It may be a simple resistor, it may be more complicated than that, and if there is absolutely no reaction happening, it is broken. So, this circuit can be used to evaluate. So, let us say I have one situation where I get a spectrum that can be modeled by a circuit like this, and I can fit it and I get values for this. This may be 10 ohm, this may be 100 ohm, this may be 20 microfarad. More or less same situation, I change the solution or I add something to the solution. Everything remains the same except this 100 ohm becomes 120 ohm. So, now I can say, okay, because I added this chemical, this reaction has effectively slowed down. Something has happened, the change in the elemental value, I can think and say, okay, maybe this is consuming some of the reactant. I have to come up with some interpretation based on what is happening in the system, what I think is happening in the system. And in order to do that, first we need to know which circuit is the correct circuit to use. We need to identify the which is the correct circuit to use, and how many elements should we use? Should we use 2 white elements, 3 white elements here? Do we need to use white circuit? Do we need to use ladder circuit? Do we need to use something else? That is one. Here I can't keep adding n number of elements, right. Then sometimes it will fit well in one representation, it will not fit well in another representation. And theoretically, if you know that these two are actually same representation, you know that it is more of the software issue. Initial values in the software is the problem, not the model is not fitting well in one case and it is fitting well in the other case. That means, I have two equations. Imagine I have an equation which goes like this is one form. it is another form. So, if you give x and y data, I can create a new data called xy, I can create a new data called x square, and I can write it as capital Y equal to a plus b capital X. I can fit it. If I use this format, it may say I am not able to fit well, this is a poor representation. That is not correct, it is just that maybe the initial values are not correct and it is going to a local minimum and saying it is not converging. I can't say I can get the data to fit this format well, but this does not fit this, because we know these two are equivalent. Likewise, in the circuit you should know which one are equivalent. Can we in theory say that these two are the same? Same meaning the numbers are of course different, but I can't say that it fits one of these correctly and does not fit the other one correctly. Okay. So, I want to show you some examples. These data are of course generated using MATLAB, you can use any language and get this. If it shows a semicircle and you want to say it is a semicircle when these are equi-scaled, 25, 20 ohms, 24 ohms in x and y direction, they have the same length, and it starts at 0 at the high frequency, you can represent this by one white element. In this case I have generated it using this value, so I know I can fit it using these values. If the value is offset, high frequency value is offset, you will have to add a resistor to that, and this is usually what you will see, at least in the high frequency, this is going to start like this and come here. Okay. For electrochemical system, this is what you would see, a semicircle with an offset. If I see two loops, this is one capacitive loop, this is another capacitive loop. I can't add another capacitor in parallel because these two can be added together. These two are basically elements in parallel and can be represented by one capacitor. So, this circuit is the same as this circuit. I need to add a pair here meaning a resistor and capacitor to model this. So, I originally have this circuit here to represent one semicircle. I can add one more like this, that is a possibility. I can add one more as this, that is also a possibility. Of course, I can add in the ladder format, I am not showing you here, but all of this will give you data in this format. So, all of this will be able to model this equally well. So, I can choose a Maxwell representation and say this works well, this will be able to fit the data. If I see 3 loops, I would say I can use C2 R2 and then 2 more RC pairs. Now, here I have shown you data where we have well separated loops and clean data. Visual observation will not always work, right. I have taken a circuit like this where I have C, R and then one Maxwell pair. Depending on the value of R3, C3 and R2 and other parameters, I can get a loop like this which is shown in the brown color. I can get a loop like this which is shown in the green square. And out here if you look very carefully, it is not one loop, it is actually 2 loops, but visually when you look at it, you can say it looks like a distorted semicircle. So, you can't arrive at the conclusion by visually looking at it. You can look at this loop, this data and say I can't model it as one semicircle, that is clear. I need minimum of 2 semicircles to model this, but I may need more. I will have to really look into that. Okay. So, how many elements should we use if you are given a data? So, what I have done is to synthesize data with some noise. This is a data synthesized with random noise added. So, you can see it is little ugly. I can take this circuit, initially I will model it only with R1, C2 and R2. So, one semicircle, Next I will add one more element, I will remove this, I will say I will add R3 and C3. Next I will say I will add R4 and C4 also. So, when you use a software to get the values, the best fit values for R1, C2, R2, C3, R3, etc., when you go through this iteration, software will give you the best fit parameter value, and usually the commercial software will also give you the confidence in each of these parameters. Okay. I will see if I can do this now. Let me take a data, any one of the data, I do not know how this is. Okay. This is a Zimpin software. I have taken some data, I have not even gone through this before. I will fit it to a model, and I will fit it to a simple model, and each software will have its own way of telling how this is arranged in series or whether it is arranged in parallel. So, in this case it is R normal brackets CR. If you go to another commercial software, they may have a different representation, they may have plus slash in one of the software, does not matter, you learn the syntax of that particular software, it is fine. I do not expect it to fit well, it will fit poorly, no problem, and in this case I can see or view the results by clicking here. Thing I want you to note is this is the parameter value R, this is the final parameter best fit parameter value C and R, and relative standard error is less than 1% here, it is 240% here, it is 10 power 18, it is just way too high, it is a poor fit. You can visually see that is one, but you should also be able to get the confidence interval values. And in this case, if I restrict it to R2 C2, right, I get the values that I have a semicircle with only R1 C2 R2 and I get 22, 95, 16, it will fit, and you have reasonable confidence in this, it is less than 5%. Considering I have added noise, this is not too bad. If I add one more R3 C3, look at the confidence, it is good, 1%, 1%, 3%, less than 6, less than 3, and I have actually generated using 20, 100, 10, and then if I remember it is 50 and 10. I have generated using a circuit which has R1, C2, R2, R3 and C3, but I have added some noise. Let us see what happens when I try fitting it with another Maxwell pair. Looks good, I get some values here and they have poor confidence, and look at the value, it is 23 kilo ohm, which means this is going to be very high resistance, it is not really contributing to the current at all compared to the current passing through these values. So, I should say probably I should stop at R3 C3. Here I should not just keep adding elements. This is one way of looking at it, there is another way, you have to look at the confidence interval. In addition you have to look at the residual sum square, meaning when you fit to a model, you get the difference between the model and experiment in the real part and the imaginary part, square them, that is the residual, you square them and add them together. Okay.
Sir, is it not necessary that with the different arrangement of the elements we get the same result?
You will get the same result, but not by adding one Maxwell pair. That is R1 C2 R2 will give you, let us say, a set of impedance. By adding R3 C3 I can't get the same value.
No, I am saying that right now you are adding in parallel.
Yeah.
If I add the rest of the part in the,
if you use a White series,
yeah,
or if you use a ladder series, ladder is another representation. If you add it in a different location in the circuit, that is what you are asking, right. Instead of this, can I add like this? And call this as R1, C2, R2, C3, R3.
Yeah, or if I get the result same from both the circuits,
you will get the result same. This circuit If it fits well to this circuit, I can show you an identical fit, not approximately equal or roughly equal, identical fit with this. Of course, the values of C2, C3 will be different, but these are equivalent. I will show you the example a little later. But physically, which circuit do you think represents your system better? Meaning, physically, can you interpret the results better?
But you said that we should not go with the visualization. I mean, just you can't say with the graph that this will be the circuit.
With the graph, you can't tell how many pairs you need.
Sir, but this equivalent circuits is just an analogy to prove that the data is at KKT compliant.
No, that part is over.
So,
Right now, what we are doing is to fit it with circuit and see whether you can physically interpret the data. Meaning, if I have a metal here, I may have a thin film here, okay, and I might think it's porous, reactants can go through it, it can react here. I might use a circuit saying this resistor, this and this, I can show like this, and then say any change here is because of the change in film quality. I am doing different methods of synthesis or whatever. That is one way of representing. I can look at another case where I get data from a reaction with no film, nothing, in which case it may be better to represent it by a ladder circuit and assign it goes through an intermediate path, that is, it reactant does not go to product directly, it goes through an intermediate stage, and what happens here is related to what happens to the intermediate. Although if it fits this circuit, it will fit this circuit also. Okay. I will give you another example.
So, but the circuit what we will choose is what will be that? It will be simplest one?
No, first thing, you need to have some idea about your system and then come up with a model of that. When I say visualize here, I mean think about the system and see which circuit is probably a good representation. Okay. Now, remember this, let us say this is electrolyte, this is an electrode, this is a double layer, and we expect a very simple reaction to happen here. A standard redox reaction is the K3 FeCN6 to K4 FeCN6, okay, with electron transfer. This case, I know that reaction can be represented by a simple resistor. So, I can say this double layer capacitor, this is the resistor and this is the solution resistance. I have physical meaning assigned to this resistor, I have physical meaning assigned to this represents the reaction and this represents the double layer capacitance, and this would give me a semicircle here. The same semicircle can be modeled by another circuit. Whatever data I get from this, I can model by this, model with this, but I can't assign solution resistance to this, I can't assign reaction to one of this, it becomes more difficult to interpret this data. So, when we choose a circuit, two or more circuits will fit the same data. Which circuit do we use? Depends on what is your understanding of the system, what do you think should be the correct representation of the system. You should be able to come with a logical explanation and say here, for example, I would say this will represent the solution resistance, this will represent the reaction impedance, that is reaction will not occur at a infinitely fast rate, it will occur at a finite rate, and I can adjust that by adjusting the DC potential. So, if I take this and adjust the DC potential, only this will change, capacitance will not change, the resistance, solution resistance will not change. If I move the reference electrode away from this, only the solution resistance will change. So, I can interpret it. Here, when I move the reference electrode from the working electrode, both will change. So, just because the circuit can model this data does not mean this is the appropriate circuit for that situation, physical situation. On the other hand, I can give you a board with a variable resistor here, a capacitance here and a resistor here. Now, if I change the resistance, only this will change. So, you have to have some idea about the system. You can't just take this data and say this circuit fits it, therefore, I will interpret it. It is like telling that I have a UV visible spectroscopy, I have done the experiment, I got data at 400 nanometer or 450 nanometer, the absorbance is 0.3, not good enough. You can get the same color at a particular wavelength, you can get the same absorbance from different chemicals. You can get potassium dichromate, it will give you orange color. I can give you orange dye, that will also give you orange color, right. I can't tell anything about the system by just saying this absorbance at this wavelength is so much. I need to have some idea. I may have a reacting system where the color changes because of particular reason. I need to say this chemical is consumed or this chemical is produced. So, independent of all this, just by looking at the spectrum, all that you can tell is this is KKT compliant or it is not compliant, without knowing what the origin of the data is. The rest interpretation, you will necessarily have to have some idea about the system. Yeah, go ahead.
But is it the right way to go with the software only?
Meaning?
I mean, in the software there are the specified circuits.
Yeah.
Okay, so if somehow we can find a new circuit, how we will confirm that this is the right way to go with this circuit?
You mean new element or new circuit?
Complete circuit. I mean, if we are making in the series ladder type or
Yeah.
something, but if we find something else new, how we will
Most of the software will give you flexibility to add your own circuit. Okay. Some software also give you flexibility to add your own element, meaning here R is a resistor. So, at all frequencies it is going to have one value. C is a capacitor for which the impedance is given by this. You can also say I will come up with a new element, I have some understanding of this phenomena, I will come up with a new element where the impedance is given by I am just making up this story. This is a new element, physically I can justify this, this is the impedance. Some software at least will give you the flexibility to add this element and then say this is the circuit, this is the new element and this is how I will interpret the data and then ask it to fit it. If they do not give you, you have to write your own code to do the optimization. Okay. But you better have a good justification for coming up with any new element. Most of these things have been analyzed well. I do not want to say you cannot come up with a new element, but it is not trivial. You can add more elements, meaning like I can add one more pair of resistance and capacitance, that all the software will allow you anyway. Now, whether you want to add or not, you really have to think about your system and see whether it is justifiable. If it fits well with 4 white elements, you can repeat the experiment, confirm yes, it can be fitted only with 4 white elements, data does not fit with 3 white elements or 2 white elements. I need to come up with some interpretation to tell why it needs so many. I do not know if I am answering your question, but okay. Now, whenever I add more pairs, usually my residuals will go down. I will fit it better, okay. But think about it, I have an equation, imagine a quadratic equation, cubic equation, a polynomial, I fit it to linear, I get a residual. I add one more, it becomes a quadratic equation, the residual decreases a lot. I add one more, residual decrease a little, probably not worth it. I can't say it keeps decreasing, therefore, I will keep adding more. So, there is a proper way to do this. N is the number of data points and I keep adding more and more parameters. Okay. There is a criteria called Akaike information criteria, and when the data points are less than 40, not data points are less than 40, n by k. If I have 50 data points, I have 2 parameters, 3 parameters, 4 parameters. When it is less than 40, I need to use a slightly different formula. It is called corrected AIC, because This has some assumptions which is suitable for large number of data points. So, I can calculate the residual sum square, multiply that by number of observations. This is sort of a penalty. If I keep adding more and more k, n remains constant anyway, the residual sum square will keep decreasing, but at some point the penalty for adding more parameters becomes too much. So, I can't just say RSS keeps decreasing, therefore, I will keep adding more numbers. And this is a corrected formula which is usually what is applicable for us, because impedance data set normally you will have 40, 50, 60, 70 data points, not like thousands of data points. And if I use this, I want to show you here that if I use this with only until C2, you have 3 parameters R1, C2 and R3. Residuals are large and you get some value for AAC. If I add 2 more, it becomes 5 parameter, there is a drastic decrease in residual and AAC is low. If I add one more pair, you have to trust that I have done the calculation correctly. Okay. Residuals are more or less the same, but the AAC is increasing now. So, if I look at the number of parameters versus residuals, it will decrease and remain flat. If I look at the AAC versus number of parameters, it will look like this, and I have to choose something which is close to this. So, that is looking at it in a statistical way and then saying that beyond this I should not add more set of elements. Okay. Tomorrow we will look at examples where I take the Symfony software to model some data and show you some cases where it works well, some cases where it does not work well, and when it does not work well, what is the way to make it work well. Okay. We will stop here today.